Well, we're nearly there, folks. Welcome back, everyone. Hope you had all a great spring break. Almost there. They really don't like us to start before it's time. There we go. Welcome back, everyone. Well, for today's class, I'm not going to try to go really too fast. I realize we're all coming back from a break in various states of tired and so on. But any questions folks would like to discuss just to start us out? Okay, well, for the things we left off on before going to spring break, I purposely tried not to go too far into assignment number 9. Or section 7.2 relative to that assignment. But if you decide to work on it early, you probably have already completed that assignment. And we're going to just do a couple more problems inside there. So this one will be due April 2nd. From there, we're going to move on to section 7.3, which will make a pretty good start today, and we'll be finishing off when we come back on Thursday's class. And I should mention, just as a word of warning, section 7.4 was definitely a fluff section for us. If we had enough time in the course, we would like to cover it. There are some really wild trigonometric identities in that section, but they're not used very often. And so we're going to skip section 7.4 and go to 7.5 afterwards. So once we're done with section 7.3, all of our efforts will be in section 7.5 to finish out chapter 7. After that, the rest of the course is going to be looking into as many applications as we have time for, coming in chapter 8. Standard ones we'll hit for sure are things like law of sines, law of cosines that could be used in other courses, and then anything else that we have time enough to get to. Well, any questions at all, folks, before we get started? Okay, well, let's take a look at where we left off on. We were here. That's kind of a rough page to come back to right after the spring break. But we were looking at the so-called addition formulas, or sometimes called the sum and difference identities. The way I highlighted these is just to illustrate the pattern of how they all come together. For every single one of these, you can really break this up into a couple groups. There's the sine group, and inside the sine group, if you memorize the first formula, sine alpha plus beta, your pattern goes sine cosine, cosine, sine. And your alpha and beta always get inputted in that same exact order. Again, this is just to aid in memorization when you're looking at these. And memorization is important because, well, the more you memorize, the easier the exam is going to be by far. It just makes you more fluent in working with these kinds of formulas. The next grouping goes, once this, there it goes, it kind of slowed down on us. The next grouping goes like this. For the cosine, the reason there's yellow highlighting is, well, there's a couple changes. It'll go cosine, cosine, sine, sine on both of them. But the plus sign is really kind of nasty on this one. It's a reversal of expectations. For the plus, you go to a minus, and if it's a minus, it goes to a plus. Like before, if you memorize, that is really weird. I have a weird slowdown on Microsoft Word. If you memorize just this line and look at the trick to get to the line down below, then that's an efficient way to get these memorized and get working with them in a fluent way. But before we get too far, let me see if I can close something to make Microsoft Word run better. Hopefully that helps. So those are our formulas. These are also important identities as well, alpha plus beta and tangent alpha minus beta. The way I typically memorize these is, take a look at the numerator. In a certain sense, it almost looks like the numerator distributes through, although that's not the right thought and function notation. It just kind of looks like it. You're splitting into two tangents coming from right here into the numerator. If it's tangent alpha minus beta, you do tangent alpha minus tangent beta. Whatever your sign is in the numerator, you flip the sign, go 1 minus and multiply your tangents. Again, here to here, the sign just flips and you multiply your same tangents. So there's a lot of different patterns and things you could take a look at to help with memorization on these. And what we did was we found out how to calculate things like cosine pi over 12. It's kind of a fun adventure on that thing. And do other things like with tangents and simplification kind of problems. A lot of these kinds of things, all we need to do is write down the identity we're about to use and then just plug in the right information. We ended class on looking at a cofunction identity that finally explains why cosine is named co to the sine function. because it's really just a phase shift by pi over 2. But for the problem we left on, we're going to prove this identity right here. So this is the problem we left on right before the break. Any questions or comments, folks, on anything of the material up above? Sorry, say again. Oh, gotcha. There's actually a formula exactly like this one in section 7.3. So kind of what we're doing on this one is we're previewing the identities already in the next section. But that's kind of the nature of trigonometry. It turns out these 4 identities right here are massive. They are the explanation of why there are so many other identities in trigonometry, because you can reformulate these in loads of different ways. And that's what we're about to do with this identity. It is a trigonometric identity, so we have to start on one side and just start working it until it looks like the other side. And it's a weird one because it turns out the left-hand side is the easier side to work with. So let's begin by saying left-hand side is sine 2t. Our objective is to make it look like the right-hand side, 2 sine t cosine t. And we don't have a lot of tools to make this work. So all I'll do is state the addition formula. Sine, let's go, alpha plus beta is sine alpha. Cosine beta plus cosine alpha sine beta. It turns out this identity right here, the very first addition formula, is the required tool to get that sine 2t to look like that, 2 sine t cosine t. That's really weird, but let's see how to make it happen. In order to really use this formula, you have to have 2 different angles, an alpha plus a beta. That was part of the things that we were doing on the very first problems, like pi over 12, where we're splitting into 2 angles. It could be a 0, but if we put, say, a 0 here, yeah, we would probably have an issue with a 0. But if we're trying to get a t and a t, another thought is, and it seems silly in a way, you could write this as sine. Instead of a 2t, just like the very first problem we did, or split it into 2 angles, why not t plus t? I mean, that works, right? If you combine those, you have 2t inside there. And now this is going to play the role of alpha. That will play the role of beta. So we're going to put in this formula on the right-hand side and say it's equal to sine cosine, leaving placeholders for the moment, plus cosine sine. Then we go back here. We know we're putting in alpha into the first slots, beta into the second slots, and we're only being careful just because, I mean, it's a good idea to be careful in a harder problem. But here it's both t and t, so it's irrelevant. It's going to be t in every single position. So here it goes. Sine t cosine t plus cosine t sine t. Well, any questions, folks, to that stage? Now, this looks weird. I have to be completely honest with you. But it turns out what we have on the right-hand side are like terms. It really looks like this. For sine, think of this as a s. Let me put it right here. Think of that as a s times. For cosine, you could put in a variable c. And over here, it's a variable c times a variable s, taking the entire role of sine. But whether you call this s times c or c times s, they're the same term. You could rewrite it as s times c plus, switch this one around, c times s is the same as s times c. Other more obviously like terms, you have 2 copies of s times c. We're going to do the same thing over here. It's sine times cosine plus cosine times sine. So overall, we have 2 copies of sine and cosine. Which portion? Oh, yeah, you could put parentheses around here, absolutely. Sorry, say again? We are done right at this step, absolutely. In fact, we could even just drop the parentheses because it's just three different numbers being multiplied. We can associate the first two, last two. It does not because there's a multiplication right here. So you wouldn't have to have just a parenthesis unless you're putting a two in, say, like that. Now you need a parenthesis overall in that setup there. But for just multiplying or combining the like terms, you wouldn't need a parenthesis on this down here algebraically. But like we mentioned, that is the right-hand side, RHS, and so the verification is complete. All we really had to do is take an addition formula, work it in a weird way where both angles are exactly the same, combine like terms, and we're done. It's just I would never have thought to use the addition formula right here to start. This is a hard one to even start sometimes. Well, any other questions or comments, folks, on that last identity here? Okay, well, this identity has a name. This one's called the double angle identity. It's called the double angle because instead of t, you have double t, 2 times t. And if you need to bring that into terms of sines and cosines, this is the identity that makes it happen. This is one of those identities that gets used all over the place, whether you're in a calculus class, differential equations class. This one comes up a lot. It's kind of weird in that way. But we did it, folks. That's the addition formulas, sum and difference identities. Any last questions about this section before we take a look at the next? It says compatibility mode up here. I'm not completely certain what that means, but let me know if any of the notes ever look weird, and I'll definitely come back and fix them. I don't think I've ever noticed compatibility mode before. But let's save this up. And now we're in section 7.3. We're not going to try to run through it really rapidly. I know it's the first day after the break. I did want to point to a couple things. This document here, Trigonometric Identities, this is like the overall document for the course at this point. We now have basically everything on the table when we're going to this section 7.3. So let's take a look at it. It's an important document to take a look at since we've been mentioning certain identities you do have to know for the purposes of the exams. So I highlighted those in yellow. Definitely the Pythagorean identities are the major ones. This is how trigonometry is even defined right here, the sine and cosine functions. And when we go to this page, this is the sum and difference identities from right here that we were looking at in section 7.1. Going down further, we're now looking into double angle formulas, half angle formulas, and reduction formulas. So all of this from here to here, that's section 7.3 we're about to take a look at. Because they're not highlighted in yellow, these would be formulas provided on a real exam. But the more of this stuff you can memorize, the easier a real exam is. These exams can be tough if you have to dig and look for the right formula that fits the right situation. If you're really familiar with the formula because you've memorized it, all of that work becomes much, much more easier. Let's open up those notes. And here's how section 7.3 starts. It begins with, well, this identity that we just proved for the double angle formula. And there's a whole bunch of other identities that's on this list. And let's see, just for the sake of maybe taking some time with this one, let's do example 1 below and spend some time with these identities just absorbing the information. So there's a couple of them that I would consider to be the major ones you want to take away from. That would be this one and this one. When people say double angle formulas, they're usually thinking about that identity here and that identity. There's also one for tangent, which is helpful, but it's mostly there for the sake of completeness. And it makes us wonder what's going on with those two. Those two are just as valid as double angle identities, but we would pretty much only use these two because they're useful to prove an identity. So if we have an identity that requires us to eliminate cosines, then we can make that happen by using this one. we need an identity to eliminate all signs, we could use that double angle identity for cosine 2 theta. So the double angle identity for cosine is a bit annoying because of that issue. There's 3 versions, but the one highlighted is the one that people usually think of when they say double angle formula for cosine. The one down here for tangent is also pretty nice, but I'd say it just doesn't get a lot of use. It's here for completeness, like we mentioned. Now, we proved this one by just using the double angle formula for sine, and I'll leave this up to you if you're curious. You can prove that one by, sorry, I said double angle formula for sine. You use the addition formula for sine on this one, use the addition formula for cosine on this one, and you get the same result. Let's see if we can prove this one right here, just for the sake of practice with all of this. So let's show cosine 2 theta equals 1 minus 2 sine squared theta is an identity. Which means it would be true for every single value of theta, because the domain on theta is all real numbers on this one. Any questions, folks, before we give this one an attempt? Okay, first thing we want to do is put down the addition formula from section 7.2 for cosine. That addition formula goes cosine alpha plus beta. Now the pattern for this addition formula is you do cosine cosine, then a minus because of that portion, and sine sine. So we'll go cosine alpha, cosine beta, minus sine alpha, sine beta. So that's the identity we're going to use. And let's begin with the left-hand side. It's cosine 2 theta, and just recopying the same technique we used in the last section, we could reformulate this as cosine beta plus theta. So now when we look at this identity that we just wrote down, alpha is going to take the role of theta, and so is beta. Again, so far it's the exact same identity that we proved. It's just the one for cosine now we're using. So coming down, I'm going to write down this portion. It goes cosine, cosine, minus sine and sine. But all of our inputs are theta every single time, so we're just dropping theta into every one of them. Feels like deja vu. But this time something is a little different happening. We proved this identity by combining like terms. We just got 2 copies of sine times cosine. Here, we're not combining like terms at all. They are not like terms. We're combining like bases. Cosine times cosine is just cosine squared of theta. And I almost put a plus there. That's not quite right. Minus sine and sine becomes sine squared of theta. But we didn't prove what we wanted to prove. We're trying to show this identity. All we got to is that one. So the problem is now boiling down to, how do we get from this to that 1 minus sine squared theta? So we're trying to get to that portion to show the identity. Without scribbling on it, let me fix that. Any volunteers for what we should do next to try to get to minus 2 sine squared theta? He was kind of suspicious in a way, but I think we can make this work somehow, some way. One thing you might try is, well, if we're trying to get to this identity, what's the problem? Well, that cosine squared is the problem, right? We have to eliminate it. There is no cosine squared there. Good news, you can always eliminate cosine by using the ordinary Pythagorean identity that reads cosine squared theta plus sine squared theta. Sorry, say again. This sign right here. Oh, this one right here. on sorry, say again? So no, we got negative sine squared, and this one's negative 2 sine squared. So we need to get two of these all together. And we also need to eliminate that cosine squared theta all at the same time. So yeah, there's a lot to do on this thing so far. But all we know for sure is there's no cosine squared. So my goal is to eliminate this right here through that identity. We can say cosine squared theta is equal to 1 minus sine squared theta, and just hope for the best. This one looks kind of foggy to me for some reason, but I think we're about there. Let me do a little bit of highlighting. This right here, cosine squared theta, is going to turn into this, 1 minus the sine squared theta. And so we now have 1 minus sine squared theta minus sine squared theta. So that was our substitution step, eliminating that cosine squared. Does that step make sense to folks so far? Good news is, it looks like we're about there. Combining our like terms, we have 1 negative sine squared theta minus sine squared theta for an overall negative 2 sine squared theta. And that means that's the right-hand side. We've verified the identity. So that's the right-hand side of 1 minus 2 sine squared theta from over here. And we began with nothing but cosine 2 theta. So that's how all these identities up here are being proved. Essentially, you just go to this identity, eliminate either the cosine like we just did, or if you eliminated sine, you get this as the result down below, 2 cosines instead of negative 2 sines. Same idea would prove this one. You just go to the double angle identity in chapter 1, or excuse me, section 7.2, do this kind of approach, but you're using alpha plus alpha, or theta plus theta, and that's the resulting identity that you get. What any other questions or comments, folks, so far on this one? Okay, so we've got a bunch of new identities. This is really just our first look at them. Those are the 2 major ones. And this is a verification of why this one ought to be true, and the one to the right as well. But here's what a typical homework problem would look like for these kinds of identities. Let me make sure we are grabbing those identities. Let's try out to example 1 now in earnest. So it says, well, we have some really odd information here. We have cotangent at an angle x is 3. X is greater than pi, less than 3 pi over 2. That sounds like quadrant 3 altogether. We want to calculate 3 different things: sine of 2x, cosine 2x, tangent 2x. Well, again, these are the major identities that we would want to use. And we're about to see why this one is really just here for completeness. You actually don't need that identity to calculate tangent 2x, but we'll see why that's going to happen. First thing we should do, though, is if you're going to calculate sine 2x, notice you need to know the value of sine theta and cosine theta, or sine x, cosine x. So let's start right here and say for step 1, find sine x, cosine x. Now, we could use Pythagorean identities to make this happen, or we could use SOHCAHTOA. Let's use SOHCAHTOA since we haven't done it in a while. Now, if people are curious, I can show you how to use the different Pythagorean identities to walk through it. So we're going to do this using right triangle trigonometry, which has the mnemonic SOHCAHTOA. So here's how it's going to go. Cotangent x is 3. I want to use the TOA part and just say tangent x is the reciprocal, so it's 1/3. You don't have to do that, but that's the acronym I usually like to use, so I prefer dealing with a tangent. Just take the reciprocal of both sides, and you have the same information. Next, I'm going to draw a right triangle. This right triangle is extremely dangerous because we still have not used this information. Let's put that in red, just as a good reminder. The outputs that we get here are not necessarily correct unless we think about the quadrants. And that's one way that the Pythagorean identities, even though it's way longer, are sometimes beneficial. So first we're going to resolve it here, bring in the quadrant information to get the right signs. We need to put down an x somewhere, and tangent goes opposite. So the opposite of x will be at value 1 over adjacent. So the adjacent side of x will be 3. So we have a 1, 3 triangle so far. Does that make sense to folks on that very first step? Okay, we need to complete the triangle, so we need to solve for this length C over here. This right here? Not necessarily. Law of cosines would be if this right here was not a right triangle, not at 90 degrees. So law of cosines would be if I have like a 30 degree, 20 degree, 40 degree triangle, something really awful like that. Yeah, totally. So this information right here means the actual triangle I'm building really lives in a unit circle that goes about like this. I was trying to get that vertex targeted to that right there. So we're going to use that information to say both your sine and cosine are going to come out negative in the very end. Does that make sense at the moment? But there is another approach. We can also use Pythagorean identities as well. So although this is a pretty confusing approach, you can take cotangent x equals 3 and work it this way. Cotangent theta squared plus 1 is cosecant squared theta. You can use that to solve for cosecant squared. Then from there, you can solve for your sine function, and then you would use sine squared x, or that's a theta, plus cosine squared theta equals 1. From there, you would solve for cosine x. In fact, that's the way I typically would do it. Let me show you how that approach went a while ago. This was somewhere in the past. We did a trigonometry session in the summer. Those are usually pretty wild. I would only say do a summer class if you know you've got a lot of free time. And in this section, here's how we actually did this problem. So same exact problem as before. Step 1, I use that Pythagorean identity, cotangent squared x plus 1 equals cosecant squared x, and I got a sine value, -1 over root 10. That gives us the sine we need here, but we still need the cosine. So in step 2, second Pythagorean identity, plug in your sine value, solve for cosine, and now we have both. And then everything ran through just as we expected. Now I'm going to do the weird trick, since I felt like people were not liking this as much based upon grading homework. This was a pretty tricky approach. That's why this semester, we're going to do it a weird way. Let me know how you feel about this. This will be a good kind of a test problem. The benefit of this is it is pretty fast. And the downside is it's tricky because x is not a 90-degree angle. It's greater than 180 degrees, less than 270 degrees. So we also have to fix this once we resolve it in the right triangle here. Well, any other questions at the moment before we give it a try? I agree with you. But the first thing we need is a value for c. And we can say that c squared equals 1 squared plus 3 squared. Sorry, say again? I'm not too sure on this one. Let me keep on going. C squared would be equal to 1 squared for a 1, 3 squared for a 9. So we've got c squared is 10, and overall, c would be equal to a root of 10. So a root of 10 goes here, and now we can almost get sine and cosine, except we need to go back up there and analyze the unit circle diagram for this. So let me go and write in, where is x really? Well, pi is in this location. 3 pi over 2 is down here. I don't know exactly where x is. All I know, tangent of x is a third, so I'm just going to draw it kind of randomly. Let's just throw it in like that. So this rotation is x in radian measurement. And now what we can say from this portion, let's use this color to make it pop. The cosine value is negative. That's the first coordinate. And the sine value is also negative. So when we go to use SOHCAHTOA, we have to include those negative signs to get the right answers out. That makes sense so far to that stage? Definitely kind of weird at the moment. Sorry, say again? In this triangle, yes. But also notice when you let x go from 0 to 90 degrees, all your values repeat across a unit circle, except your signs change. So what I'm going to do is use the repeating nature of sine and cosine across a circle, pull in the right sign changes, and SOHCAHTOA will still work on this problem, as wild as that seems. Let's give it a try, and if we like, we can compare the other way of doing it with what we did, well, I did in the summer a while ago. So let's start off, SOHCAHTOA would be that sine at x is the opposite divided by the hypotenuse. The opposite is 1, hypotenuse is root 10, but then, like you're mentioning, Michael, this is not the full story because x was not an acute angle. It was in quadrant 3, and sine in quadrant 3 pulls in a negative sign. We must get negative 1 over root 10. But let's take a pause right here and compare with what happened back in the day. Back in the day, what I did was use this Pythagorean identity, cotangent squared x plus 1 is cosecant squared x, took the value of 3, squared it, added together, and you got a 10. You know what? That already feels like deja vu in a way, that root 10 there. Then square root both sides, you get pluses and minuses. It resolves to a negative sign because we're at quadrant 3. And take the reciprocal of both sides, you get negative 1 over root 10. It wasn't a coincidence that we got the same thing here, despite the fact the angle is not acute. That's a really kind of a weird process. And again, the whole purpose of using SOHCAHTOA here is, if you can streamline all of these Pythagorean identities, it might not be a bad idea. Does that make sense to that stage so far? Definitely wild. And in all honesty, I'd say for the purposes of good practice, this is the better approach. It just takes a long time to get through all that kind of stuff. But knowing how to use this identity in step 1, that identity step 2, that is valuable work. So if you decide to do it that way in the homework, I'd say that's a great way to do it as well. But let's keep on going. We're now going to the cosine function. So cosine of x through SOHCAHTOA will be the adjacent side, which is 3, divide by the hypotenuse, which is root 10. Then this is a really dangerous step, like we were mentioning. That diagram is not perfect because the angle is here and cosine should take on a negative value. Looking at how it went in the past, we got the same exact stuff. So let's screenshot this and call this method 2. I'll just drop it here and call this method 2 for example 1. So if you'd like to run through that different process, here's another way to do it without SOHCAHTOA. It looks horrible in all honesty, but it is good practice to see it this way as well. But either way we do it, sine has to be negative 1 over root 10. Cosine has to be negative 3 over root 10. And when you do this much algebra, a really good idea is a really fast check. Recall tangent's supposed to be 1/3. Let's use these and see if we really get a third. Tangent x would be the sine value. Here it is. Divide by the cosine value. Dividing means we multiply by the reciprocal. And when we multiply these through, the root 10s cancel, the negative signs cancel, and we do in fact get to 1/3 as required. So that tells us, hey, we're on the right track. We are getting the right values for tangent based off this method. Well, any other questions so far, folks? Okay, now what's really wild about this problem is, folks might have noticed, we haven't even gotten started on any of this. This whole problem was about getting your sine and cosine value just so you can get to the point where we're actually using our brand new identities. So now let's give that a try. I'll erase this check down here so the notes don't get too busy. And now let's call this sine 2x. First thing we want to do is just put down the identity. The double angle identity for sine is kind of nice. You take the 2 right here, and you just spit it out. You cannot typically do that with functions, so sine is particular. And the rest of it is sine x times cosine x. And you know what? That's exactly what we have. We have a sine x value right here, -1/√10, a cosine value. So we're just plugging them into those locations. We'll turn into 2 for sine, -1/√10. For cosine, look above, that one is a -3/√10. Now we just multiply all this together. Across the numerator, we have a +6. √10 times √10 in the denominator will give you just 10. Fraction then reduces to 3/5 altogether. This is a lot of work, but this is the punchline, so I'm going to put a box on this one, just to convey we're now hitting that actual target of the problem. We found sine 2x. Well, any questions, folks, with using the actual double angle identity down here? Okay, weird problem, because I'd say the hardest part about this problem was not that double angle identity by the red dot. It was more getting sine and cosine to begin with. Just starting it off is the hard part. Let's try cosine 2x now. And you might need a new page. Let's go down here and make it happen. So for cosine 2x, there's 3 different identities we can use, but we typically want to use just whatever seems convenient. For me, I would typically just go cosine squared of x minus sine squared of x. And then that would do the job for us. By the way, notice how dangerous this identity is, because right by that red dot, if you flip that to a positive, then the whole thing is not cosine 2x anymore, it's 1. That's kind of a wild identity when you think of it in those terms. Off by a sign means you've changed the thing in a majorly massive way. It's no longer cosine 2x. Sorry, oh, gotcha. So if we multiplied everything by -1, yeah, it'd go like this, this, and this. Exactly, you'd have to distribute through in that way, exactly. Other questions so far? Okay, well, all we're pretty much doing is grabbing this, and plugging them in. So this is the next locations they plug into. For cosine squared, I would just put in a big parenthesis like this. Good idea to write that negative in and then start with another parenthesis. We have to put these in order as well. So if I plug in the sine one first, I don't have the right answer. I'm off by a negative sign. What goes right there has to be the cosine value. So -3 over the square root of 10 goes in that position. Then for the sine position, put in -1 over the root of 10. And we did it, folks. I mean, we still have to crank it out and simplify our answer, but that's most of the fighting, getting to just that step. Continuing, we'll square -3 to get a 9. Root 10 squared just peels off the square root and you get a 10. Then definitely copy that minus. It's easy to not get the right sign in the middle because of all these negative signs. -1 squared is a 1, another 10 in the bottom, so we get 8/10, which will reduce to 4/5. So that's the second portion we wanted. And, well, any questions, folks, with that one there? Okay, so pretty much the only part that's the identity was that and that. Those are our double-angle identities. The rest of it is just plug and chug, making the right substitutions and simplifying our work. We have one last one we have to hit, and that's the tangent 2x. Good call, absolutely. That's the comment I was going to make here. You could use that identity, but you're working actually pretty hard, right? If you've already got sine and cosine at 2x, we'll just reuse those. So let's go down below and say tangent at 2x. Just like Michael said, just use the definition of tangent. It is sine 2x divided by cosine 2x. And we have just calculated those values. Yeah, that looks like an exact 3/4. Division by 5s would go away. So for sine 2x, throw in that 3/5 that we already put in. For cosine 2x, the denominator, it's the 4/5. The division by 5 go away, but if you want to show the steps, it's, oh, not that. That would be the answer. The steps would be 3/5 multiplied by 5/4. The 5s here just cancel off, and now we have 3/4, like you said. And finally, that's the last one. So we did it, folks. That was sine, cosine, and tangent, all at 2x. Any questions at all, folks, on running through these? Been trying to delete that. I think that was typed in. There we go. Okay, so that's the magical, wonderful world of the double angle formulas.
One question.
Yeah.
So how do you know the square, like when you do your negative 3 over square root of 10, and then also minus 1 over square root of 10?
How to square, y to square, like that
Yeah.
power 2? Gotcha. That power 2 came from the power 2 right here. It was the only reason we were squaring.
Okay.
And yeah, it's kind of weird because on this one, these are all power 1s. And so we had to multiply them through rather than squaring them. So just from the format of the identity was what was causing that right there. Other questions so far? Okay, then again, this was pretty wild using this approach. So this is the SOHCAHTOA method of actually getting your sine and cosine x. Probably the most confusing part of the problem was that portion, not the actual identities that we just used, those two. So if you'd like to see this done from a different route, like I mentioned, here's the second method of making it all happen. Observe, you still get the same result. It just takes a little bit extra step to get there. Well, it looks like we have time for just one more problem for the day. Still working with the double angle identities. We'll prove one more identity and then go on to call it a night. First, any questions so far? Okay, so what I've done is just recopied all the double angle formulas. I think it's always good to convey that the list of formulas I gave here is just a complete list, but we typically use those two a lot. We need a reason to use any of the other ones here. And this is an example to show when you probably might use the additional different formulas down below. So proving this identity, let's get a good look at it. Notice that you have sine 2 theta and a cosine 2 theta. So that already strongly suggests try a double angle identity. Sometimes just eyeballing the problem is the most important part because you're looking for features that tell you what the strategy could be. And it's all about that 2 theta that's directing us in this problem. So we'll start by saying the left-hand side equals, I'll just copy it first so we know exactly what we're working with, sine 2 theta over sine theta. Tragically, there is no cancellation right here. Sine 2 theta is considered a totally different quantity than sine theta. So they're not like bases whatsoever. Likewise, no cancellation on this one. But that's okay. We have tools available for us. Let's see which ones we really want to use. Observe the right-hand side is just a secant, which is reciprocal of cosine. That means over here, we're hoping to eliminate sine. We don't have a lot of choices on this one for sine 2 theta. This is it. I have one double angle identity for sine 2 theta. It goes that way. So we'll start by writing in for this location by the red dot, that is equal to 2 sine theta cosine theta, all of which is divided by sine theta. Let me highlight in yellow where we made that substitution. Then go minus cosine theta on the denominator for that second fraction. But on this one, we should be extra careful. Because sure, this is the one we use a lot, but sometimes in identity proving, you might not want to use that one. We put in cosine squared minus sine squared, you now have a sine to deal with, but there are no sines on the right-hand side. This one's probably a bad idea for this particular situation. This one's an even worse idea because it only involves sines. But this one looks like it's exactly what we want. We put that identity there, we get only cosines, which makes sense because that is a 1 over cosine. There's no sines available. So it's for that reason and that reason alone, this time we're taking cosine 2 theta and inputting 2 cosine squared of theta minus 1. I put parentheses around that because we need to distribute that negative sign in as well. So highlighting above, those are the double angle formulas we actually used. Now we're out of ideas. We have to hopefully simplify and get to a secant. But notice what we can do already. There's a cancellation, sine and sine. Didn't work here because it was 2 theta versus theta, but here the angle is the same. We really can cancel. So this is turning into, from that first fraction, 2 cosine theta. And we need to do a little bit more algebra on this one. I'm going to do 2 things at once. The sine is going to distribute it in, and cosine will divide. So you will get minus 2 cosine of theta, or excuse me, cosine squared of theta, divide by cosine theta. So that's our first term. Then it does it again. This negative sign distributes here, flipping it to a positive one. And then cosine will divide into that positive one as well. So this will turn into plus 1 over cosine of theta. Exactly. It sounds like we're in the right track, right? 1 over cosine theta does conflict with what we want, that secant there. We just hope that all of this cancels off. If it does, we're home free, right? Let's take a look at it a little bit closer and hope for the best. We have cosine divided by, or excuse me, cosine squared divided by cosine, and you can do a cancellation. This cancels the power, so it's just negative 2 cosine theta. Let me write in as another step just to clarify it. After canceling cosine over cosine by the red dot, we now have 2 cosine theta minus 2 cosine theta, because the power is now a 1 after cancellation, plus this one we should write as a secant theta. And that means we're essentially done. These are like terms. If you have 2 cosine theta, take away 2, you've got no cosine thetas. All that's left is secant of theta. And that was the target we were trying to hit all along, the right-hand side. That means we did it, folks. The verification of this one is complete. Pretty much the main takeaway with this problem is just more practice with the double angle identities, where you see the yellow highlighting and the green highlighting. But the bigger takeaway is sometimes you do want these other weird looking identities, but it's usually you're proving an identity that required a specific one to speedline it, or streamline it rather. Well, any other questions, folks, before we call it a night? I feel like this was a pretty rough section to be in, coming right back after spring break. Sorry, that's how the cards just fell this time. We'll definitely be in a better shape to look at these ideas a little bit further when we come back on Thursday. But have a great night, folks. If you have any questions, I'll be happy to help out. Otherwise, I'll see you all on Thursday's class.
Thank you.
Yep, have a good one. Let me double check. If I don't, I certainly can provide it. And for exam 2, oh geez, it looks like I did not provide that. Let me put down a note and I'll get back to you on that. What I'll do is I'll post it right here. And I'll also email you to let you know. Exam 2. I think what happened was I started grading them after the break and I just totally forgot that that's what I typically do on the Moodle site. But what I do remember is folks did pretty good on that one.